Welcome to tutorial 4.2, part 3 and 4. This is again on writing precipitation reaction equations, but this time we're going to write ionic equations instead of molecular equations. So up to now we've been writing molecular equations, but it's sometimes useful also to write ionic equations, that is to show the ions the way they actually exist in solution. So what do ionic equations show? They show the soluble strong electrolytes as ions. So you have to identify which substances are sitting in the solution as electrolytes, as free ions floating around independently, and just designate them as such. The ionic equations with the spectator ions omitted, so if we don't show the spectator ions, the ions that actually don't do anything, they don't actually join together to form a precipitate, that's called the net ionic equation. And you'll just see in a way of a few examples how this works. So look at the first example here. We have silver nitrate and sodium chloride, and we mix them together, and the question is, what's the precipitate going to be, and how do I write the ionic equation? So I first highlighted here in red the possible precipitates. Is it silver, that's positive and a positive ion? Will it join with the chloride that's negative, or is it the nitrate ion that's negative that will join with the positive sodium ion? And if you remember right from the solubility chart, it's the first one is what forms a precipitate. That is, the silver with the chloride is not soluble, so that forms a precipitate. Sodium and nitrate, sodium is an alkali metal, it's going to be soluble, and nitrates are always soluble, and there are no exceptions on our chart. So we identify it as the silver chloride, that's the precipitate. So what are the spectator ions? Well, the two ions that do anything, they just floated around, and those are the sodium and the nitrate ions. So how do I write the net ionic equation? I just showed the two ions that actually join together to form a precipitate. Silver plus chloride forms silver chloride. It's all balanced, and that's all there is to it. All right, so let's look at another example. How about this one? Lead nitrate with sodium chloride. And again, I look at the two possible combinations, the new combinations that are possible. Is it the lead with the chloride that forms the precipitate, or is it the sodium with the nitrate? And kind of notice I highlighted here in red the actual ions that might join together. So there's no need here to put the sub 2 in your thinking as what might join. We're just saying, is the nitrate ion, that negative 1 ion, will it join with the positive 1 sodium ion? The answer is no. As we just saw in the last example, sodium and nitrates do not form precipitates, but lead chloride does. So again, we've identified the precipitate as lead chloride. What are the spectator ions? Once again, it's sodium and nitrate. And the net ionic equation is just the lead joining up, in this case, with two chlorides because of the charge difference. A single lead with a +2 charge will attract two chlorides to itself to form a lead chloride crystal. All right, that's another example. Let's do one more. How about potassium sulfate with potassium sulfate with barium chloride? Again, what are the two possibilities? Potassium with chloride. And again, notice I did not highlight the 2 next to the potassium because the potassium has a +1 charge, and it would join, if it does, with the -1 chloride. Or is it the sulfate with the barium? This time it's the second of the two choices. It's the barium and the sulfate that forms a precipitate. It's just because it's insoluble. Therefore, the spectator ions are the potassium and the chloride, and the net ionic equation shows the barium and the sulfite coming together to form barium sulfate. I think that might be it. Now it looks like there's maybe one or two more. This time we write the whole thing out. Okay, so here the example is write the molecular, the complete ionic, and the net ionic equation for the entire reaction. So not just the net ionic. Okay, so we start in the same way. Potassium iodide and lead nitrate. I highlighted here the precipitate already. It's going to be lead iodide. So the next thing for us to do is now write a complete molecular equation out like we did back in section 4.2 part 2. So we combine the new combinations. We say, all right, so the new combinations are potassium nitrate and lead iodide. And then we go ahead and balance the entire equation. That's the molecular equation. So what's different about this and the ionic equation? The ionic equation is going to actually show the individual ions the way they exist in solution. That is, these potassium iodides, they're actually not joined. They're freely floating ions. Same with the lead nitrate, and the same with the potassium nitrate. However, over here, the lead iodide, those are actually in the form of a solid. Therefore, equation or the formula is written is not misleading. So notice what happened. The two potassium iodides here are written as two potassium ions and two iodide ions. And be careful, if students make a mistake here, is that they forget this 2 in front of the iodide. Remember that 2 refers to the entire potassium iodide as a unit. Therefore, there's both 2 potassiums and 2 iodide ions. The lead nitrate, there's a lead ion with a +2 charge. And again, notice, if this was forming some kind of solid, we would show the empirical formula as 2 nitrates for every lead. But to show the independent free-floating ions, the nitrates are not joined somehow, so you wouldn't put an NO3 sub 2, but instead you put the 2 in the front to show there are 2 separate nitrate ions floating around per lead nitrate unit. This one over here, the last one again, the 2 potassiums, probably most people get right. It's the 2 nitrates. They tend to forget this 2 in the front, but remember there's 2 nitrates because there's 2 potassium nitrate units. And don't split up the lead iodide because those exist in, exactly as indicated as a solid 1 lead ion for every 2 iodides in a solid crystal. All right, that's the ionic equation. What's the net? Well, you just cancel the spectator ions that are on both sides. Those substances that didn't do anything, and we can tell what those are. That's the potassium and the nitrate. So this potassium we wouldn't bother writing, and this nitrate we wouldn't bother writing. Therefore, on this side, these 2 ions are floating around. Just don't write those. And there we go. That's the net ionic equation. And typically, you'll put the positive ion first if you want to. It's just an aesthetic thing. There's no reason you can't write it this way. All right, let's do one more to make sure we're pretty good at it. Magnesium nitrate with sodium hydroxide. I've highlighted already the precipitate that's going to form. So let's go ahead and write the molecular equation. And notice, and don't make this mistake here, the hydroxide, that you're going to need 2 of them to go with the magnesium. I kind of already indicated that by putting a 2 in the front. That was just because I copy and pasted it from before. In any case, you make the magnesium hydroxide. That's the thing that is the insoluble precipitate. Sodium and nitrate is not going to be insoluble. Those are spectator ions. So that's the molecular equation. So now we can go ahead and again write the ionic equation. Let's see if we can get this straight. 1 magnesium, but 2 separate nitrates. Since they're separate, I got to put the 2 in the front. Here, the 2, make sure that you carry it for the sodium and the hydroxides, 2 sodium ions and 2 hydroxides. Don't mess with the magnesium hydroxides. Those are that's the precipitate. That's what actually forms. And on the other side, we have 2 sodiums and 2 nitrates. Those will be the spectator ions. And so in the net ionic equation, we don't bother writing those. All right, I think that's it. Good luck with this. I think it should be okay for you. If you have trouble, well, of course, like always, practice again in class. All right, good luck. See you in class.